Hello students, today we are going to take up the next topic, that is application of integrations. Now, in the previous chapter we had done the fundamental theorem of calculus, then we did all the results for finding the indefinite integral and ultimately the definite integrals. So let us now see the geometrical interpretation of definite integral. Now suppose we have to find the integral I is equal to integral from a to b fx dx, where y equal to fx is the curve something like this. So we draw a rough sketch of y equal to fx, x equal to a to b. So let's draw what is x equal to a. X equal to a is a line parallel to the y-axis, and x equal to b is also a line parallel to the y-axis passing through x equal to b, and this is the x-axis. So when we write integral from a to b fx dx, we mean the area enclosed by this curve, the x-axis and the lines x equal to a and x equal to b. Effectively what we do is we draw a thin strip of thickness dx. And why do we use a thickness dx? Because it's a small increment. Suppose this is a line which corresponds to y equal to, it corresponds to a point x, so this y will be fx at this point. Give a small increment dx to this x along the x-axis, so that the thickness of this strip would be dx. The height of this strip would be y, and the upper end of this strip is along the curve, whereas the lower end of the strip is along the x-axis. If we drag this strip from x equal to a to x equal to b in such a manner that the lower end always travels along the x-axis, whereas the upper end always remains on the curve, then this strip will cover this entire region which is enclosed between the curve y equal to fx, the x-axis and the lines x equal to a and x equal to b. But this process is nothing but finding the definite integral of fx with respect to x from x equal to a to x equal to b. Thus we see that when you find the definite integral from a to b of fx dx, we are finding nothing but the area enclosed between the curve, the x-axis and the lines x equal to a and x equal to b. Similarly, the same curve y equal to fx can be written as x is equal to some function g of y. And so if we find the integral of gy with respect to y from, let's say, y equal to c to d. So if we are finding gy dy from c to d, what we actually mean is we are drawing the same curve which now we are writing in terms of gy x equal to gy. The line y equal to c is this, and the line y equal to d is this. This is the y-axis. This is the x-axis. So what we see is that the line y equal to c and y equal to d are parallel to the x-axis. The curve is this. We draw a thin strip of small thickness dy along the y-axis. The length of this thin strip is x, which is equal to gy. As we drag this thin strip from y equal to c to y equal to d, this in such a manner that the lower end always travels along the y-axis and the upper end always travels along the curve x equal to gy. Then in this process, this covers the entire area covered between the curve, the y-axis and the lines y equal to c and y equal to d. And so, which is written in terms of definite integral from c to d, gy dy. Clearly, since the variable of integration here is y, so the limits are also of y. So, these are the two ways in which we can find the definite integral of the same curve, one with respect to x-axis and one with respect to y-axis. And this is how we are going to do the questions based on it. So basically the steps steps required to find the area under curves. So what all we are going to do, we will plot or draw a rough sketch of the curve. Then we either find or are given the limits of integration. Then we can find the area enclosed by the curve and the x-axis or the y-axis as the case may be. Okay, now one thing you have to keep in mind, that is, suppose you are finding the area under the curve. Let's say the curve is somewhat like this. Okay, and we want to find from x equal to a to x equal to b, which lies somewhere here, and this is the x-axis and this is the curve y equal to fx, and this is the origin and this is the y-axis. So basically the area required is this area, that is area 1, and this area 2. So the required area will be equal to a1 plus a2. But when you see here, when you draw a thin strip here, this corresponds to the height is y into dx, whereas when you draw a thin strip here, the y coordinate would come out to be negative, and so you have minus y dx. So when you find the integral, this will a1 comes out to be positive, whereas a2 comes out to be negative, which is not possible because area is never negative. And when you add a1 plus a2, instead of getting added, what you get is difference of the two areas, which will give you wrong results. So we have to be very careful that in case a portion of the curve lies below the y-axis, or in case you are finding the area in some manner like this. Let's say you are finding the area between the y-axis and the curve. So here it is on the left side of the x-axis, so that the area gets subtracted. What we do is we have to keep in mind that we can't take the negative value of x here or negative value of y here. To overcome this problem, what we do is we simply find area is equal to a to b modulus of y into dx. Similarly, if you are finding with respect to y, you can do from c to d modulus of x into dy, and this way we will be able to deal with the negative sign of the value taken up by y here and the value taken up by x here, and we'll actually get the magnitude of the area rather than with sign. So basically we always take the positive component of the area. Like for example, if we take exercise 8.1, so what we get is in exercise 8.1, suppose we have to find the area bounded by the curve y squared. First question says y square equal to x and lines x equal to 1 and x equal to 4 in the first quadrant. So first of all, we'll do a rough curve tracing. That is, we will first draw this curve. As you all know, depicts a parabola. Parabola symmetric about the x-axis. So what we do is we draw the curve. This is y squared equal to x, or if you are writing it as y in terms of x, it will be y is equal to square root of x. We are taking positive x because here this portion we have to do only in the first quadrant. Then we draw lines x equal to 1 and x equal to 4 here. So basically the required area is this portion which we have to find out. As I had already mentioned, what we do is we will be drawing a thin strip of thickness dx. It has to be, and this is y. So this has to be dragged from x equal to 1 to x equal to 4 to cover this entire area. And so the required area will be y, which is this, into dx, which is this. This is the area of the rectangle. This, when gets integrated from x equal to 1 to x equal to 4, it covers the entire area which is required. So what we do is dragging this strip from x equal to 1 to x equal to 4 such that the lower end always drags along the x-axis and the upper end always drags along the curve. This is the same thing as finding the definite integral of y dx from x equal to 1 to x equal to 4, and this can be easily solved. 1 to 4, we know the value of y is square root of x and then dx, and using this, you know the results of integration. You can solve the integral as this is x raised to half, which comes out to be 3 by 2 over 3 by 2 from 1 to 4. So many square units. Whenever you are finding area, you will always write square units along with it. So it means that the first thing, in order to find the area under the curve, you need to know the curve tracing. Like you have to have some rough idea about the curve, the kind of curve which you are dealing with. Because unless and until you draw a sketch, you are not required to draw a proper sketch, but at least a rough sketch which gives you an idea about what is the area which you are finding. And accordingly, you will get some idea about the limits because of the fact that you are able to trace the curve properly. Okay, so what we do is, let's do a few points to do curve tracing. First thing is that if you have y equal to mx plus c, always represents a straight line. Okay, which straight line having slope m and having the y-intercept c units. This we had done last year. Now going in this manner, if as a result of this we know that x equal to a constant is a line parallel to y-axis, y equal to constant is a line parallel to x-axis, then we have y equal to x can be written as y equal to 1 into x plus 0. It means it's first thing, the constant is 0 means c equal to 0 means line passing through origin. Okay, and y equal to x means here. In this case, m equal to 1 means slope, that is tan theta equal to 1, that is theta equal to pi by 4. And so it's a straight line making an angle pi by 4 with the x-axis, and so it is symmetric about both x-axis and y-axis. So y equal to x is symmetric about both x-axis and y-axis. Okay, now then next thing which you will see is, if you have any curve, let's say which a curve having only even powers of y, x may or may not be in even powers. So any curve having only even powers of y is symmetric about x-axis and vice versa. For example, if you have y squared equal to 4ax, it has y only in even powers, x is in odd. It's an equation of a parabola which is symmetric about the x-axis. If you have y squared equal to minus 4ax, this is also a parabola but symmetric about the negative x-axis. This is symmetric about the positive x-axis. All this we did last year. Now similarly, if you have x squared equal to 4ay, here x appears only in even powers, y is in odd. So this is symmetric about y-axis. Okay, because of this positive sign, this one is symmetric about the positive y-axis. Whereas if you have x squared equal to minus 4ay, it will be symmetric about the negative y-axis. This is x, this is y, this is origin. Similarly, if you have both in even powers, let's say x squared plus y squared equal to a squared. Now the standard form, this is an equation of a circle. Standard form of equation of a circle is x minus a whole squared plus y minus b whole squared equal to a squared. Now when you open this, you will have both x and y in even as well as odd powers, and so this represents a circle with center at a, b, and radius is equal to r square with radius as r. So this is symmetric, not symmetric about x or y axis. Whereas if you have it having center origin, right, now this is a circle having center at origin and radius equal to a units. Now this is symmetric about both x and y axis. Reason being, both x and y are purely in even powers of x. Same way, if you have a equation of this is also a circle plus y squared equal to r squared. Clearly when you open it, you will get x squared minus 2ax plus a squared plus y squared. So here y is purely in even powers, therefore symmetric about x axis. And when you actually plot this, so what do you get? This is a circle having center at a comma 0, a comma 0, and radius as r units. So clearly there is symmetry about the x-axis. Similarly, we have the circle which is x square plus y minus b whole square equal to r square. When you open it, you will have x purely in even powers, whereas y is in even and odd powers both. And so it is x purely in even powers, it implies symmetry about y axis, and this has the, it's again a circle having center at 0 comma b, and so it is symmetric about, and radius is r units, it is symmetric about the y axis. Okay, now same way we have done already the ellipse and hyperbolas are both symmetric about both axes as they deal with only even powers of both x and y. The ellipse is something like x squared over a squared plus y squared over b squared equal to 1, where it is horizontal ellipse if a is greater than b, and it is, if it is in the form b greater than a, that is the denominator of y squared is more than a, then it is vertical ellipse. Same way here we have hyperbola. In this case, if it is x squared over a squared minus y squared over b squared equal to 1, purely even powers, but here the positive term decides whether it is an about like the parabola is about the x-axis, and here it is a horizontal hyperbola, whereas if you have it as this, that is the y square term is positive, we have the hyperbola somewhat like this. This is called as the vertical hyperbola. In both the cases, these are symmetric about both x and y axis. So these are some of the points which you have to keep in mind before doing the curve tracing, and then accordingly you can do the questions of the exercise 8.1. So just try it out, otherwise I'll be taking up in my next video. Thank you.